This course introduces similitude and approximations in engineering. There is a famous story concerning the first explosion of atomic bomb, the Trinity test in New Mexico, USA on July 16, 1945. The plutonium device named the Gadget was tested. The yield of this explosion was a very well-kept secret. However, the USA released a few pictures several years later, pictures of the explosion and the mushroom cloud that was formed. These pictures contained the timestamp from the time explosion and a scale. A British scientist named G.I. Taylor was able to estimate the power released from this bomb by using similitude calculations. Using purely dimensional arguments, he showed yield of the bomb as 25 kilotons of TNT. The other examples include a Saturn V rocket which was used in the Apollo space program for landing in the moon. This rocket was 110 meters tall, weighed 2,800 tons and costed $185 million. But before this rocket could be used for manned space flights, one need to be very sure that this rocket would work. So tests have to be done, and the tests were done on small rockets. A smaller version of this rocket was made and was tested in various manners, in a wind tunnel for finding out the forces, in a dynamic testing ring to find out what are the vibrations that go through this rocket when the fuel inside this sloshes. Another example where the present course could be useful would be to determine the design of piping in process industry. We can show that the pressure drop across a pipe is a function of length of the pipe, diameter of the pipe, the roughness of the wall of the pipe, and the density and viscosity of the liquid. So while you are designing the pipe, the theory is not complete. We need experimental results. So we have to do experiments on every little pipe of different length, diameter, epsilon, rho, and mu? No. It can be shown that instead of delta P to be a function of 5 independent parameters, we can cast using the similitude theory so that the non-dimensional pressure drop is a function of 3 non-dimensional groups instead of 5 non-dimensional groups. And this reduction permits us to write delta P by rho g as F times V average square by twice G L by D, where now F is a function of rho V average D by mu and epsilon by D alone. So 2 parameters only, and if there are 2 parameters, this can be summarized in one chart. So given a Reynolds number and the relative pipe roughness parameter epsilon by D, we can find out what is the friction factor from one chart. That is considerable savings in effort. This course would establish the procedures for reducing the number of independent parameters that go into designing experiments. We also will talk about in this course the basis of approximations. If we predict the global weather using thousands of equations on a supercomputer and someone suggests that we're making a mistake by not including the effects of the flapping of the wings of a distant butterfly, several weeks earlier, we would simply have laughed it off. Why? Because engineers believe that the small causes produce small effects. And to their way of thinking, the flapping of the wings of the butterfly is a small cause. But what is a small cause in general? So there are procedures that have been set for determining what is a small cause. We will show that in an oscillating boundary problem with a fluid between two plates in which one plate is oscillating, we will show that we could divide the field in two parts. In one, there would be the effect of viscosity, in the other, there would be no effect of viscosity. This and similar approximations would be dealt with in this course.